Hello and welcome to another video. In this video we're going to continue on with these on-sites, so I'm going to be doing the Amazon one next. And going to try to do the same thing, clean code, dry runs, no mistakes, stuff like that. So let's get going. Okay, given the root of a binary search tree, enter k, return true if there exist two elements such that their sum is k. Alright. So the obvious solution that comes to mind is get every element, put it into a list, and then do like a two-sum. I guess we can go with that. Yeah, might as well. Okay. So we'll go like values, do a DFS. Alright. Then from here it's basically just a two-sum, so Alright, let's go with this, see how we do. Okay, so let's do a quick little dry run, not too much here. Alright, so we're gonna have this traversal, yeah, essentially. Yeah, I'll just go through the values in some order, it doesn't really matter. Yeah, so we're gonna have a 5, we're gonna check for a 4, no 4. 3, check for 6, no 6. 6, check for 3, and we got it. Alright, next one. So we're gonna have a 5, check for 23, nope. 3, check for 25, nope. 6, check for 22, nope. And yeah, you're basically just gonna get no for any of these. Alright, pretty happy with this. We just need to call traverse. Alright, and then once again, as long as we don't make any major mistakes, good enough. First root. Oh, misspell. Alright. Cool. Alright. Given string contain 2 to 9, return all possible letter combinations. Mapping. Okay. Alright. I think this is pretty straightforward as well. We're just going to make a dictionary of the number and the letters it represents, and then for every letter, we'll try every single key and then do like a backtracking. Yeah, seems good. Okay. So, map or mapping or whatever this is. So, I forgot how you do this in Python. I don't know if you have to give it a string. I think you do. So 1 will map to nothing, actually. 2 will map to ABC. 3 will map to df. I think this is how you do it. Yeah, I think in JavaScript you don't need to give it a string, but I think here you do. We'll find out. 4 this and so on. 5 that. 6 oops 7. Yeah, I don't think there's like a shortcut because some of these have 3, some of these have 4, and so on, so I think this is actually just the fastest. Okay, have a result and a cur, and just do a basic backtrack. I. So we're gonna go through digits and try everything. So if I equals length digits, result append join cur, standard backtracking template, return. All right, now we're gonna go through all the keys and add them to the cur. So I guess first, okay, yeah, so it only has 2 to 9, so all of these do have something. So for car or something in mapping digits I, cur append car, backtrack, pop, and that's it. Okay, call backtrack on 0, return res. Pretty confident this will just work, so I'm gonna skip the dry run, but we'll see what happens. Yeah. Okay, so I did think this would work for the empty string, so what do we get for the empty string, I guess? Okay, so I guess for the empty string we just want to have nothing. But that's fine, like empty string, or that's a small thing, so we can write that as well. So if not digits, return this. That's not a big problem, I think. Nice. Alright, given a linked list n such that each node contains an additional random pointer or null, construct a deep copy. Deep copy should contain n brand new nodes. Okay, both in next. Okay. Alright, so okay, so essentially we want to make a copy of this thing, and then I think what we want to do is for every node in here, we can essentially make a map of like old node to new node. Are all these values unique? No. Okay. Now, can you put a linked... Can I use a list node in a dictionary? I don't know. Let's Google that. List node as a key in Python dict. Not super sure there. Can be. Correctly hashable. Okay. Interesting. I think this will work then. Yeah, we'll find out. But essentially, if this is doable, if you can map the old node to the new node, we're just gonna go through all the new nodes, or all the old nodes, and build them first. So we're gonna build a new node for every old node, and then we will copy the pointers. So in the beginning, like, we're going to have this list, right? So 7, 13, 11, 10, 1. So we're going to do one traversal, just build the copies of this. So this will be like copy of 7, copy of 13, copy of 11, copy of 10, copy of 1. Then we're going to go through the nodes again, and we're going to check like what is its next node, and then we'll make the new node point to that next node. So like 7 points to 13. So this 7 will point to this 13, and so on, because we're going to have a mapping of old node and new node. Let's go with that. And then we are going to return the head of the new linked list. So can we have no nodes? Yes. Okay. So if not head, handle that case. Now we're going to say current equals head, and we're going to make this mapping dict. And we're going to say while cur mapping dict cur equals node cur val, and that's it. And we're going to leave the next and the random null for now. Let's say cur equals cur next. Then we're going to do one more loop. Cur. Okay, now what we want to do is we want to say mapping dict cur next. So we need next and random. So next, is going to be mapping dict. Sorry. This is the new node. I guess we can probably even write that. Yeah, so we can say like new node equals mapping dict cur. Now new node next equals mapping dict cur next. New node random mapping dict cur random. Now we just go cur equals cur next and return the mapping dict of cur. So essentially we're making all the copies, and then we're just gonna have basically a pointer of old node and new node, and then we're gonna make these things. Yeah, we're gonna make these pointers. So like we'll make a copy list and we'll say like, okay, 7 points over here. So whatever this points to is what the new 7 points to, and so on. All right, let's go with this. Once again, don't need a dry run, I don't think, assuming this works. Find out. Key error, none. Okay, can random point to null? So I assume no. I see. So if random points to null, then, okay. Gotcha. So in that case, we have to say if cur next in mapping dict. No, actually we have to say if cur next exists, right? And same thing for if cur random. Okay, so if they exist, then they should be in the list. All right, now let's try this again. Still getting none, interesting. Return mapping dict cur. And what node are we getting that for? We're getting that for which test case? This first one, I guess? Oh, right. That's typo. Okay. Alrighty. Okay, good enough, I think. Ah. Okay, it looks like we might have a record speed. So this one I've just done recently, and it's pretty simple. All we have to know to figure out how much water we hold is how much water, like what's the height of the node next to it. So the height of the node is the actual height of the node plus the water it holds. So if we're on this node and we know like what's the height of this, like if we know this holds this much and this holds this much, then the node is going to hold the minimum of those two. And the way we can figure that out is we can basically just, so for a node, like the amount of water it's going to get bounded by, actually I didn't think about that. Maybe it's not. Maybe I forgot about it. I haven't done this exact one. I've done something else. Yeah, I guess the way I did it, we could do the same thing I did, actually. So what we could do is we can basically store two walls in a, like a, whatever, some kind of data structure. Yeah. And then the height is going to depend on the smaller wall. So I guess let's walk through this example with this. So this first one has height 0, and then this last one has height 1. And then let's just say there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so there's 10 nodes between those, so we're going to write that. So we're actually going to only store the height and the index, and then we'll just like close in. But what we can do here is we can say, okay, so the walls for sure can't hold anything because the water just flows out. Then we're going to close in from the smaller wall because, like, if you have a container, and let's say this container's left wall looks like this, and the container's right wall looks like this, and we have something in the middle here, the middle is going to flow out depending on which one is smaller, right? So in this case, this is how much water we hold. So that's kind of the idea here. So basically we're going to say, okay, since this wall is smaller, and then let's have a result variable as well. We'll have it equal to 0. So because this wall is smaller, we're going to move this in first. So if this is 0, that means this can hold, like this won't hold any water basically. This will hold 0. But we have to keep track of what's its height as well. So it will hold 0, but its height is 1, right? That's this cell here. And then we do this. So now it doesn't matter which one we move in because we have this wall and this wall. So let's say we just move in again this way. So now we move in and we're going to say, okay, well, its left wall held 1, its right wall held 1. So the most it can hold is 1. And it has 0, so it will hold 1. And result is 1 now. So this is 1, this is 1. We can move in any way we want. Let's say we move it from the left again. So the most this cell can hold is 1. And it has height 2, so it'll hold nothing. So now we have a height 2. Now we're going to move in from the right because this was smaller. So the most this can hold is 1, but it has height 2, so it'll hold none. Now we can move in just left again, let's say. So the most this can hold is 2. That's this guy here. And it will hold 1 because its height is 1. And it can hold 1, right? So the most it can hold is 2. Its height is 1, so it'll hold 1 more. And its height is 2, so this is 2. Let's go from the left again. We're on this cell now. The most it can hold is 2, and it's empty, so it will hold 2. And its height will be 2, so 4. The most this can hold is 2. So 2. And its height is 1, so just 1. Okay, now we're on this cell and this cell, I believe. Yes. So now we're going to move in this way, let's say. So the most this can hold is 2, but its height is 3, so it'll hold nothing. Now we're going to move in from the right. So that's this wall here. The most it can hold is 2, but its height is 1, so it'll hold 1 more. And then now we're on these two, I think. Yeah, I think that's it, right? Because everything else, yeah. So I mean, we can move in again, I guess. So we'll move in here. The most this can hold is 2, but its height is 2. And then we'll move in here, I guess. Or actually, no, we're basically done. Like once we can only move into empty walls. So essentially something like that is the idea. So all we need to do is store the left boundary and the right boundary, and then we just like keep moving in until we get to, until we get to a cell that essentially like we're gonna start at like 0 and then like the length of the heights or whatever. And as long as there's something in between those, we can keep going. If there's not, then we're done. So if this is like 0 and 1, let's say, then there's nothing. So yeah, okay. So result 0, our array will be, so I guess what do we want to store? I think we want to store the index and how much water, right? So it's going to be like index or total height, water, and height. So total height. So we'll do in this format: index, total height. Cool. Okay, so we'll say this will be our like container or something. Okay. And I think this is optimal, and I don't think I've done it before this way. So yeah, good that I understood it from doing the harder one. Okay, so yeah, so this is index 0. The total height it can store is just whatever the height of this guy is. And the other one is length height -1. And then whatever that thing's height is. It can't hold any water, so just whatever that is. Let's just go this. All right. Let's go h-1 and height h-1. All right. So while C0 is strictly smaller than C1, and this is the index, so C0 is 0. All right. So this is basically going to be an O1 space solution and linear time. Okay. So yeah, so then we basically are going to say like which one of these is smaller. So if this difference actually has to be, this difference has to be greater than 1. Like if this is like 0 and 1, then we're done as well. So I guess we'll do this. This has to be greater than 1. Okay. So if C10, which is the actual value, is greater than C0, or sorry, like this, right? The height is what we want. So if the 1 is greater than this, then we're gonna move right. So we're gonna go C0. We're gonna update that. Yes. Okay, so how do we update that? So let's just get some values here. So I guess the water, or like next index or something, right? So like next index equals C0, 0 plus 1. The water we can hold there will be that thing's height. So we'll call this like Ni or something, or I. The water it can hold is going to be height of I. And the most it can hold is going to be, let's see. So if we have these two walls and we move in, then it's going to depend on the smaller of the two walls, right? Yeah. So this is going to be C01. So this is the smaller of the two walls minus the height. And we can max this with 0 because like if it can hold 2 but it has height 3, it obviously can't hold negative water. So we'll max this with water like that. All right, now we can update this guy. So we can go C0 equals the new index, which is I, and then it's going to be height plus the water it can hold. So let's see here. Yeah, so it's going to be C, or actually, yeah, not C. It's going to be height I plus the water it can hold. That's going to be that. And result water. Otherwise, we're just basically can do the opposite of that. So C10 minus 1. The water will be the smaller wall, which is here, minus height I, C1. All right. And yeah, kind of already did a dry run, so let's see if we missed anything. Might have some small stuff, but pretty happy with this. Nice. Did we get it right away? Ooh, awesome. Yeah, definitely, once again, if this was like a competitive programming, I would have skipped all that explanation. Could have done this in like 10 minutes faster, but... And yeah, so I'd say, let's see. This one I haven't seen before. This one I have seen before, but it's not a hard problem. This one I have seen before as well a while ago, but it's also pretty easy. Like, I think these are on the easier side of a medium. This one's also not too hard. Like, yeah, once you realize it's just a smaller wall. Also, the way I did it was more complicated. The end space solution is even simpler. So, yeah, kind of, I'd say, an easier side overall. Yeah, 22 minutes, 4 problems. Average 5 minutes, not too many mistakes, very small. Pretty happy with it. So, yeah, let me know what you think. Let me know how you like these videos. And then, yeah, I think I have... How many more? So we did this one. So we have 1, 2, 3 to go. Yeah. We'll see you in the next one. Thanks for watching.